In this online lecture, we're going to discuss the relative intensities of molecular ion peaks and how we can use them to figure out what might be present in our unknown molecule. So what we're going to see here, number one, is that the relative intensities on the mass spectrum, they correspond to the relative abundance of isotopes. We're also going to see that number two, there's a nice formula that works here, that we can calculate the number of carbon atoms in a sample by taking the relative intensity of an M+1 peak and dividing it by 0.011 times the relative intensity of just the plain molecular ion peak. And three, we're going to see here that M+ peaks or molecular ion peaks can indicate if a compound contains an atom or atoms other than carbon. So let's start with understanding our first key point here. Let's just say this happens to be the mass spectrum of pentane. Remember, we learned in a previous online lecture that the heaviest peak most likely corresponds to the molecular weight of the molecule, and it just so happens that pentane does have a molecular weight of 72. But notice, look up close here. We can actually see that the 72 peak is not the heaviest peak. There's another little peak right here, and it happens to be 1 unit bigger than 72, which means it's 73. This right here is called an M+1 peak, which simply means the molecular ion plus 1. How is it that we're getting this heavier peak? Well, it actually goes back to general chemistry. Remember, carbon comes in two isotopes, carbon-12 and carbon-13. And you might remember from general chem that the relative abundance of these two isotopes are 98.89% to 1.11%. What did this mean? Let's say you happen to have a bunch of carbon atoms in your hand. If you were to inspect each of these atoms, you would notice that 98% of your sample has carbon that weighs 12, and about 1.1% of your sample would be carbons that weigh 13, hence the term relative abundance, the abundance of the carbon-12 relative to the carbon-13. So let's go back to our spectrum here. What this means is, for instance, look at our pentane right here. It has 5 carbons, and there's a great chance that all those carbons happen to weigh 12. And if that is the case, this entire molecule would weigh the 72 grams per mole. And of course, that corresponds to this signal on the mass spec. But what we're seeing here is that it's also possible for one of our pentane molecules to be this. Notice one of the carbons in this pentane happens to weigh 13. Remember again, when we're running molecules through the mass spec, we're running a lot of them. So there is a chance that if we have a whole mole, let's say, of pentane, that one of them would be the pentane on the bottom here. If this bottom pentane is run through the mass spec, then because that is carbon-13 there, this molecule would have to weigh 73 grams per mole. It is this pentane right here that is giving rise to that M+1 peak. Now, you might be wondering, well, is there a chance that we could have a pentane molecule where 2 carbons are carbon-13? Well, remember the relative abundance. Remember, out of a sample of carbon, 98% of it is going to be carbon-12, and only roughly 1.1% is going to be carbon-13. So the chances of one pentane molecule having 2 carbon-13s are slim to nil. But there is a chance that one of the carbons could be carbon-13. So that's what's happening here. That's why we're getting an M and an M+1 peak. Now, it just so happens that because of this fact, there's a nice equation that we can use here, and it looks like this. Notice, on the left-hand side of the equal sign here, we have number of carbon atoms. That's always going to be equal to the relative intensity of the M+1 peak divided by 0.011 times relative intensity of the M peak. Meaning this, we're going to be able to take the mass spec M and M+1 peaks and use them to figure out the number of carbon atoms in our sample. Let me show you how to do this. Notice the formula is asking for the relative intensity of the M+1 peak. That means what you can do here is, let's say your M peak is 100%. Then we measure here to see how tall the n+1 peak is relative to the M peak. And let's say it happens to be 5.5%, meaning if you took the height of the n+1 peak and divided it by M, it would be 5.5%. That happens to be the numerator of our equation right here. However, since we're plugging in a percent, we got to plug it in its decimal form as 0.055. Now, the last thing to take care of is the denominator here, the relative intensity of the M peak. Well, remember, that's the one we set as 100. And again, putting him in decimal form gives us a value of 1. And notice, performing this calculation right here, this happens to equal 5. And remember, we know that our sample here is pentane, and notice it does happen to have 5 carbons. So this is a very valuable formula to use. However, this relative abundance analysis that we're doing here is not limited to carbon. For instance, let's check out Br here. It just so happens that Br comes in 2 isotopes, Br79 and Br81, and the relative abundance just so happens to be 50.69% is Br79 and 49.31% is Br81. Remember, these percentages are laws of nature. So what does that mean if we happen to have an unknown substance that has a Br? And let's say, again, we put it in the mass spec, we shoot an electron beam at it, and it just so happens to dislodge this electron right here on the Br. We would get this result right here. And since this molecule is missing an electron, the overall charge would be positive. And this substance, of course, right here would give rise to our molecular ion peak on the mass spec. And where would that peak register? Well, this molecule just so happens to weigh 122 grams per mole. So let's look at the mass spec here. Notice that's exactly what we see here, an M peak at 122. But notice we see another peak here. This peak happens to weigh 2 more units than 122. So hence he's called an M+2 peak. And notice for a second here the relative heights of these 2 peaks. They're roughly the same. Why is that so? Well, let's go back here. Remember, this is our substance that we're putting into the mass spec. And remember, since Br comes in 2 forms, some of the molecules will have Br that weighs 79, and other molecules will have the Br that weighs 81. When we put them through the mass spec and shoot the electron beam at them, and let's say again we happen to dislodge these particular electrons, then we would get these molecular ions right here. The one on the left would weigh 122 like we saw, and the one on the right would weigh 124. The question is, would we see more of one of these substances than the other? Well, remember, the relative abundance of Br is again 50.69%, and the heavier Br is 49.31%. That means that roughly half of the substances are going to have the Br that weighs 79, and the other half are going to have the Br that weighs about 81. So we'd see them in relatively equal amounts. Hence, going back to our spectrum here, this is why they would be roughly the same relative abundance. In fact, if you actually measured their relative heights, you would see that one is about 50.69% and the other one is about 49.31%. So they're not exactly the same heights, but roughly. And what we're seeing here is the connection between relative abundance of isotopes in general chemistry and the relative heights of the peaks on the mass spec. We're seeing that there is a correlation between those two things. To make sure you got this, let's do the same type of analysis, but this time with the halogen Cl. If you remember from general chem, Cl also comes in 2 isotopic forms, Cl35 and Cl37. And it just so happens that their relative abundance is 75.77% for the Cl35 and 24.23% for the Cl37. So again, let's look at an example here. Let's say I happen to have an organic molecule that happens to have a Cl. And again, let's put him through the mass spec and shoot an electron beam at him. And let's say we just so happen to dislodge this electron right here. If that happens, again, of course, we get a molecule that has a positive charge. However, we would get two versions of this molecule because, again, remember, some molecules would have the Cl that happens to weigh 35 and other molecules would have the Cl that happens to weigh 37. The question is, are we going to see these two substances in equal amounts? Well, remember, the relative abundances are roughly 75% to 25%, which means that we would see the Cl35 molecule 3 more times than we would see the 37Cl molecule, simply because 75% to 25% is roughly 3 to 1. So we should see a peak at 78 due to this molecule and a peak at 80 due to the molecule on the right. And notice here it is, the actual mass spec. Notice we see the 78 and the M+2 peak at 80. And look at their relative heights. They are 3 to 1 or 75% to 25%. So notice this is something that's very obvious on the mass spec, meaning if you see a mass spec that has a peak at whatever value and you see an M+2 peak that's 1/3 of it, we're going to know right away that that molecule happens to have a Cl. If we see two peaks at the end of the spectrum and they're roughly the same height, then it's going to be obvious that that molecule has a Br in it. If we don't see an M+2 peak, then it's likely that that compound doesn't have any halogens in it. So let's put our knowledge to work here. Let's look at a sample problem. Let's say, for instance, the spectrum of a corresponding molecule containing a halogen has the following data. What this data is telling us is that we have an M+ molecular ion peak with a relative intensity of 51. We have an M+2 peak that's roughly 100%, and an M+4 peak at about 49. The question they're asking us is which and how many halogens does this molecule have? Well, let's take our data and look at an actual picture here. This is what they're telling us, that the M+1 peak right here, if he's 51%, we're saying that he's 51% of the M+2 peak over here, which we're arbitrarily assigning a 100% peak. And that means the M+4 peak, if it's 49%, he would be roughly the same height as the M+ peak, but of course half the amount of the M+2 peak. Now let's try to answer the first part of the question. Which halogen is this? Well, remember, we know our relative abundances of Br. It's roughly 50-50. The relative abundances of Cl are roughly 75 to 25. So right away we should know that whatever our molecule has, it doesn't have one halogen. It's more likely that it has two halogens. Again, if it only had one halogen, we'd only see an M and an M+2 peak. But in this one, we're getting an M+2 and an M+4 peak. However, the question is, which two halogens do we have? Well, if you think about this, it's more likely that this is going to be the Br halogen, simply because notice the ratio of our peaks. It's kind of like 1 to 2 to 1. Whereas with the Cl, we get the 3 to 1 ratio, which doesn't seem like it would correspond to our data here. Now, I'm not saying we know this for sure, but it seems like it's more worthy right now to investigate if our molecule can possibly have two Brs. Let's do that analysis first. If it doesn't work out, then we'll try to analyze the Cls. So, for example, let's say this happens to be our molecule, and we're assuming it has two Brs. There is a chance that both Brs happen to be the isotope that weighs 79. If this goes into the mass spec and we shoot our electron beam and again dislodge this electron, we would get this particular molecular ion. If you calculated his weight, you're going to notice that he would weigh 186 grams per mole. If that's the case, let's pretend that that's going to be our M+ peak, our molecular ion peak. However, we also know it's possible to have this molecule, where one of the Brs is 79 and the other Br is 81. If he goes through the mass spec, we should expect to see a peak at 188 grams per mole. But notice there's another possibility here. Instead of the Br on the left being 79 and the Br on the right being 81, we could have the opposite. The Br on the left happens to be 81 and the Br on the right happens to be 79. This ion would peak also at 188 grams per mole, which means either one of these could correspond to the M+2 peak. However, there's one last possibility here. Because the relative abundance of Br is pretty high for both species, it is possible that both of them in the molecule could be Br81. This ion would happen to weigh 190 grams per mole. This peak could possibly correspond to the M+4 peak. So far in our analysis here, we've seen that it is possible that if our molecule has two Brs, to get an M, an M+2, and an M+4 peak. However, we still have to check the ratios. Would it be 50% to 100% to 50%? Well, if you think of it this way, the chances of getting the first molecule at 186 is, let's say, 1. Then the chances of getting the N+2 peak would technically be 2, because there happens to be two versions of that peak. And the chances of getting the last peak would of course be 1, just like the M peak. So, going back to our spectrum right here, notice the relative abundances or ratios of each peaks are technically 1 to 2 to 1. So notice our analysis of Br landed right on the dot. If a molecule did have two Brs, it would have an M, M+2, and M+4 peak, and these would have to be the corresponding ratios of their heights. So the answer to the question is our molecule most likely has two Brs in it. So notice big picture here. Mass spec is not only delivering the possible molecular weight of a compound, but it's also telling us what other atoms might be present in our molecule. And in this particular case, the number of other atoms that happen to be in our molecule. But notice it's the knowledge of relative abundance of isotopes that helps us with this type of analysis. So it's a good idea to know these relative abundances. Notice carbon right here, first on the list. We know, remember, his relative abundance is roughly 98% to 1%. And notice we have the Cl and the Br there on the bottom of this chart with its relative abundances. But notice we can do the same type of analysis with nitrogen, oxygen, sulfur, fluorine, because we happen to know the relative abundances of the isotopes of these atoms. Now, I wouldn't run off and memorize all of these. Most professors would give you this information. Of course, unless your professor tells you otherwise. However, all I'm doing at this point is pointing out that relative abundances of many atoms are known. These are just some. So, what did we learn here? Key points. Number 1, we saw a relationship here. That number 1, the relative intensities of the mass spectrum correspond to the relative abundances of isotopes. We also saw number 2, a valuable formula that can help us calculate the number of carbon atoms in an unknown sample in the mass spec. And we also saw number 3 here, that N+ peaks can indicate if a compound contains atoms other than carbon.